Uh, so welcome all. Welcome to this fifth lecture on Introduction to MATLAB workshop, right? So till now, what we have done in the previous lecture was we begin with the introduction to programming and the need of programming language to solve an engineering applications, right? Then we learned about the MATLAB. We saw various basics command in the MATLAB, how to create our own functions. And in the last class, we learned about various loops if else functions, right? For loop, while loop, etc. Now, with this knowledge, what we will do now from today's lecture onwards, we will try to solve various chemical engineering problems pertaining to specific numerical method aspect, right? So we will start with the basic problems. Like today, we will focus on the mass transfer and mass balance and energy balance problems, and then uh, onwards we will move with the nonlinear system of equations, optimization problems, etc. Right? So till this point, I hope that you guys are trying to give some time to MATLAB programming so that you get used to and know what exactly is happening, right? So that's why the previous class were to get to get to you guys familiarize with the MATLAB so that you can work it out further problems that we are doing. So my opinion again will be that you guys try learn the basics, understand the fundamentals, so that from today's class onwards, whatever we problems that we are solving, you guys can follow that. Okay. So in today's class, what we will be focusing on is solution to linear algebraic equations. So if you recall the lecture one, in lecture one we had discussed that as a chemical engineer, we encounter various numerical equations and methods to solve different problems, right? And the basic one was the linear algebra. So linear algebra comes particularly when you solve mass balance and energy balance problem in multi-component system. So what are that examples? So if the distillation column is the best example, if you consider it. So you have overall mass balance between components going in and out. Then you have each component, individual component mass balance. Even if you want to do further detailing, then in distillation column you have multiple trace, right? So you can do mass balance at each trace stage also. Same way you can consider energy balance examples. So apart from that, we have different separation problems. So liquid extraction, leaching, all the separation problems where you don't have specific reaction happening, right? So all the unit operations you can consider that they somehow involve this mass balance and energy balance equations, right? And that too you solve multi-component equations together. So with this idea in mind, we will start with the learning how to solve this linear algebraic equation in our system, right? So if I talk about what are these linear algebraic equations, so considered this that what I mean when I say I have system of linear equations, right? So this is how it looks like, that you have set of m equations with n variables, right? So it's given as so you can consider this as a individual component mass balance across let's say distillation column or liquid extractor, right? At different stages you have. So you have mole fraction x1 x2 xn. You can consider that you have n component in your distillation or the separation problem, right? So x1 to xn represents the mole fraction of that component. This a11 a12 etc are the coefficient of your mole fractions, and the b1 to bm is the constant, right? So this is the general form. So if you will take any example, let's say and try to put the mass balance equation, what we do, input plus output input minus output plus generation minus accumulation is equal to 0, right? This is our strategy at steady state. Okay. Now in that, if you will put further component balance, you will end up with some sort of equations. And what we do, if there are few variables, we can solve them by hand. But let's say if there are multi variables, then how to solve it? Specifically, if you will look at the example of refinery problems, when you are refining the crude oil. So crude oil has multiple components, right? So there are no just even within the paraffins, there are different carbon chain lengths that you have available. So each will require a different individual component mass balance, right? So in that cases, you have multi-component system which you cannot solve by hand. So that's why we will use the programming language to solve it. Now, this general equation you can represent in terms of the matrix algebra, right? So this system of equation, I can represent it as ax uh, equal to b, where x is your variable matrix x1 to xn, right? A becomes your coefficient matrix and its dimensions are m cross n, where m represents your number of equations and n represents number of variables, and B becomes your constant matrix. It's again m cross 1, right? How many number of equations you have, that many constants you will have. So now you have equations, and if you will recall, in 11 12 we have solved this sort of equations, right? So if you have ax equal to b, then if I want to find what are the values of variable x, it will be a inverse into b, right? Correct. But uh, now when we have a smaller matrix, let's say 2 cross 2 cross 2 or 3 cross 3 cross 3, still you can do A inverse into B by hand. But if the matrix size is bigger, maybe 4 cross 4, 5 cross 5, then the hand calculation becomes much difficult, right? In that case, you cannot use this hand calculation. You have to rely some sort of a simulator or software to solve these equations. That's where we will use the programming part to solve these equations. Now, before we go to the solution part, let's just briefly recall the uh, various ideas or the various nomenclature when we solve this system of linear algebraic equation and how the solution will look like. So, if you remember, the matrix rank, it's a maximum number of linearly independent row or columns, right? So we defined in matrix algebra, we defined something called as rank of matrix, and that gives the how many rows or columns are linearly independent, the maximum number of linearly independent row or column, right? Now, based on the rank of matrix, you decide whether your system of equation will have a unique solution, infinitely many solution, or no solution. So if I have system like this where ax equal to b, and if rank of matrix A is equal to n, and then rank of A augmented B matrix is also n, so both are equal, so it's called as full rank matrix, right? So you will have a unique solution. But if your rank of A, matrix A and A augmented D, both are same, but uh, it's not is equal to n, which is the uh, sorry, which is equal to the maximum uh, full rank. It's less than n, then system becomes undermined. What does it mean? Is that let's say you have this uh, m equations, out of which there will be few equations which might be correlated. In the sense, let's say equation 1 and 2 are correlated, where if I multiply equation 1 with 1.5, I get the equation 2. So that means they are correlated. That's why they are not linearly independent. They become dependent. That's why you get rank of matrix less than the the maximum possible value. So in that case, your system becomes underdetermined. And if both the ranks are not unequal, if rank of A is not equal to rank of A augmented B, then system is overdetermined and you cannot get the solution, right? So this was the base idea. If you recall your linear algebra and the matrix algebra, you will find this. This is the very basic concept, right? So we will start with that. Whether if we have system of equation, first we have to identify whether the solution exists or not. Whether we get the unique solution, whether we get infinitely many solution or no solution. Okay. So in MATLAB, you can use rank function to find the rank of a matrix, right? So its syntax is rank of A. If you provide matrix A and type rank A, it will give me the maximum linearly independent rows or columns, right? Based on that, what problem we have been given is we have to determine the rank of following matrix and comment on whether their solution exists or not. Okay. So let's try to solve this problem. Let us consider this. Rank of matrix A and A augmented B. Sorry, I will write use of rank of matrix A and B to determine the solution. Okay. So let us consider we have been given first A is equal to 1, 2 and 3, 4. So 1, comma 2 and 3, comma 4. So this is my matrix A. Now here we haven't been provided the constant matrix B, the constant matrix B. So right now I will consider it is equal to uh, the length of A into B, right? Sorry, I will consider the size of matrix B as whatever number of rows I have in matrix A. So right now I will consider it as 1 and 1. Okay. Let's not say 1 and 3. So this is my matrix A, my matrix B. Now, if I find rank of matrix A, rank of matrix A augmented B. See here A augmented B will what it will do is it will combine matrix A and B in in column wise manner, and then it will give you the augmented matrix, right? And let's say if I run this code, solution to linear algebraic equations. So if I run the script, what will happen? Oh, sorry, it should be 2 cross 1. I created a vector, right? So I have matrix. So first, rank of matrix A, that is coming as 2. Then rank of A augmented B. So this A augmented B, what it does, it combines matrix A and B in a column manner, right? So I had matrix A 1, 2, 3, 4, and the B was 1 and 3. So it had combined it column wise, and I got this A augmented B matrix. And when I'm finding the rank of matrix A augmented B, that is also 2. So according to our conditions, what we learned was that if both have the same rank, and that is equal to n, where n is your uh, maximum of your row or column for the A matrix, right? The n is equal to number of variables. Then you get a unique solution. So if I have system with this coefficient A and constant matrix B, then its rank will be, I will get a unique solution for that, right? Now, I don't want to use it exactly this way. I mean, rather than putting it in terms of like deciding on my own, what we can do is we can set a structural programming part where we find the rank of matrix A as well as the A augmented B matrix rank, and decide whether we will get the unique solution, infinite solution, or no solution. So for that, let us consider this part. Yeah. So something like this we will do, where we provide matrix A and B, okay? And then we will use the structural programming to decide whether what kind of solution we have. Okay. So let me get rid of this. And first, what I will do is find the rank of matrix A is, so here I am printing the rank of matrix A. Now, if you recall, previously we had mentioned you can use %d, %f notation to provide any variable in the printing part, right? So same thing I am doing here. Rank is %d /n to start a new line at the end. rank of matrix A. Now f printf the rank of A augmented B matrix is %d slash n. Then I will have sorry, rank A comma B. Okay. So this will provide me the rank data, rank of matrix A and B. It should be within parentheses. Okay. Now I have to write one structured part that it will help me to decide whether the both ranks are same or not. So what I will do, I will first compare the rank of A and rank of A augmented B. So if rank of A is equal to rank of A augmented B matrix, then I will have a two option. Either I will have a unique solution or either I will have a infinitely many solution, and that will depend upon comparing this rank with the number of variables n, right? So for that we will use this portion. So I will first compare the ranks and then I will compare how many number of variables I have. Okay, so in this case here, if you will look, this is how the coefficient matrix look like, when number of row represents how many equations you have and number of columns represents how many variables you have. Okay, so if I get how many, what is the column size for the matrix A, then I can get the how many variables I will have, right? So if you recall, when we put size of any matrix A, you get this data. Okay, so size gives you row versus row and column data. If I type, let me change the matrix with a different example. So let's say 1, 2, 3. So this is my A matrix. And now when I type size A, I get 2 row and 3 column. Now if I just want to take out how many columns I have, so I can take size comma 2, it will give me only the column value. If I only want to know the row value, I can type size A comma 1. Okay, and it will give me the length value, the row value. Okay, so now I will compare. So within this first if loop, there is another if loop which says if rank of A is equal to size comma A 2, then f printf we will have unique solution. Okay, else we have to, else what option will be there? Obviously if it's not equal to number of variables, then it will be less than that. That means we will have infinitely many solutions because there are dependent equations. This secondary if loop ends within. Now first condition was if ranks are equal, then I have to check this. If ranks are not equal, right? So if ranks are not equal, that means I won't have there won't be any solution that will exist, right? So same thing I will type, if ranks are not equal, then I will type else f printf no solution, and this ends my if condition, right? So now you can check, if I run this, I will get this. The rank of matrix A is 2, rank of A augmented B is also 2, and we will have a unique solution. Okay, let me end this lines by /n /n. expression. Let's look at the other examples. So if I have matrix A is equal to this, okay. Now matrix B, it should have the same number of rows, and if you run it, so it's giving you that rank of matrix A is 2, while A augmented B matrix rank is 3. So you will have, since they are not equal, there won't be any solution because system is your underdetermined, right? So for this coefficient matrix, here again I have given provided the value of B. So depending upon the what value of B you select, obviously your answer will vary. But this is how you can decide whether you will have one solution, unique solution, many solution, or no solution. Same way you can try it out with the other equations also, right? Now this is the first idea, that when I have system of equations, to first decide whether we will have the solution or not. Once I know that solution exists, the second step will be to solve the system of equations to find out the solutions, right? So for that case, we will use the numerical methods, which are these three. I don't know if you have studied this or not, but if I'm correct, the Gauss elimination method is the part of 11th, 12th curriculum, right? So in Gauss elimination method, what we do is we convert matrix into row echelon form, and that we use it to find the solutions. Apart from that, there is LU decomposition, where you matrix is converted into lower and upper triangular part, Gauss-Jacobi iteration method also. So let us look at the Gauss elimination method. I have provided this reference, which provides you the detailed description of Gauss elimination method. So what we will do, we will try to understand first what's the concept behind the Gauss elimination method. And once we have done it, then we will try to code it out. Okay. So here in Gauss elimination method, it's a fundamental algorithm used in to solve the linear algebraic equations, right? Where you transform your matrix into upper triangular matrix through series of row operations, and then you find the variables values based on that. Okay. So here, this is the core idea. Category of linear equation system consists independent solution, dependent has infinite, and inconsistent has no solution. So first we check this part, right? Based on that, we decide whether we will have one solution, infinitely many solution, or no solution. Once I'm done with that, now, so if I have independent or dependent solution, I can work with the Gauss elimination method. Now, in Gauss elimination method, what you do is, let's say you have this two system of equations, right? And this is your A augmented B matrix. So you first create an A augmented B matrix, and then you do series of row operation to convert into the upper triangular matrix. Here it's very simple example. So in order to create the upper triangular matrix, you have to make this element 0. So for that, what has been done, that first row is multiplied with -2 and that added into the second row, so that you get the upper triangular matrix. Now once you have that matrix, you can work backwards and then compare the coefficients. So minus 5y is equal to -6, so y is equal to 1.2. Then first row says 2 times x plus 3 times y is equal to 8, right? 2 times x plus 3 times y is equal to 8. You already found y value, you substitute it, and then you get the x value, right? So this is the basic Gauss elimination method. Now, if the system of equation increases, like in this case, you have three equations and three unknown x, y, z. So this is how your coefficient matrix and augmented matrix will look like. So if you combine the all the coefficients of x, y, z, this is your matrix A, and this is your constant matrix B, and combining you get the A augmented B. And then on this you can perform. So here they haven't provided it, but here you can perform again row echelon form. And in row echelon form, what we have to do is we have to create an upper triangular matrix. That means we have to make this element 0 by series of row operations, correct? Once you do that, you will end up with some final row echelon form from where you can backtrace and compute the XYZ value, right? Uh, I hope you guys have already read it. See, this is how it will look like for another case, that you have this system of equations. You are performing series of elimination part, right? So here, so second row contains this 2, 1, minus 1. So multiply the first row with 2 and then add it into the subtract into the second row. So you get this element 0. Same way for the third row. Uh, if you will multiply the first row by minus 1 and then add it here, then this element will go 0, right? So they have, I think, made a mistake. It should be R3 here and minus R1. Same way, R2 minus 2 times R1. And you will end up with this row echelon form. Now you have this two element 0. Now next step is to make this element 0. For that, they have performed further series of operations and then created this upper triangular matrix. Okay, this is your upper triangular matrix. Now you can back trace it. So your z becomes 10. Here it's very simple. Y equals to minus 12 and x equal to 8. Okay, so this is Gauss elimination method. I hope you guys are recalling it, because I'm not spending too much time here because it's very simple method, very basic method. I'm sure you might have gone through it in your 11th 12th part, and if not, then some initial math course in your BTech curriculum also will include it, right? So this is the basic concept of Gauss elimination method to find out the solution. Now what we will do first is we will try to code it out, this Gauss elimination method, on our own, and then try to find solution to the system of linear algebraic equations, right? So here, this is the concept of Gauss elimination method, where we will follow this method, where I will use the first pivot component. So pivot components are nothing but the diagonal components, which we are referring as the pivot element. So we will select one pivot element. Let's say in this case I am selecting A11, and with the A11 value I will make this A21 and A31 as a 0. So I will perform series of operations. So what kind of that operation will be? So let's say I multiply the row 2 with A21 divided by A11 and subtract it from the second row, and I make this two element 0. Okay. Once I'm done with this part, I can move and try to make this element 0. So this is the idea or the logic behind this Gauss elimination method. Okay. And once you do that, you will end up with this upper triangular matrix that we can utilize for the solution part. Okay. So let's look into that example, that I want to create a Gauss elimination method. So what I will do, I will first create one function which creates an Gauss elimination path. Okay. Let me just copy paste this and I will explain it to the go. Right. So first this function. So I have created this function which is Gauss elimination, which converts your matrix A, whatever matrix you supply, into the upper triangular matrix UA. So my function starts with function. My output variable is UA, upper triangular matrix. Input variable is your sum matrix. Okay. Now first I will extract out its size. So size meaning, when I say size of A, I get row and column data, right? So I'm storing it this value here. In this example, when I'm typing size of A, I'm getting 3 comma 3. So this is my answer, right? Now if I want to save this, so I will say row column is equal to size of A and B. So I get this. So row is equal to 3, column is equal to 3. So that way you are storing the output data. So I'm first taking out how many rows I will have, how many columns I have. Once I have that data, so see, this is the logic. So logic says here that take first pivot element and make rest of the below it 0. So here I'm starting with one for loop for I is equal to row 1. So this is a for loop which works in the row part, creating a row echelon form of matrix A. Okay. So here first for loop is start with first row and go till last row minus 1. Okay. So this is how this loop is going. I'm starting a for loop variable I which starts with 1 and goes to final row minus 1. The next for loop, which is a J loop, it starts with the I plus 1 row and goes to the final row part. Okay. So start with I plus 1 row and go till last row. Okay. Now I am finding this multiplier. So here, see what we did first was we copied matrix A as UA. Once you have done that, I am finding that multiplier UA J comma I divided by UA I comma I. So let's say I start with value 1. Here J value is 2. So first UA, it will be 2 comma 1 and then UA 1 by 1. So this is how it will look like if I compare with this data, that I will get first UA 2 comma 1 and this is UA 1 comma 1. Now my multiplier becomes U uh, 2 comma 1 divided by 1 comma 1. Right? This is my multiplier. Think about it like, so when you want to decipher any loop or a function, what you do is, since we know the basic structure of loop, try to see how the variable is changing and what computational happens in between, right? So here I'm starting with variable I and j. So let's consider first variable. It will start with 1. I will start with 1. J will start with 1 plus 1, 2. So right now my I and j value are 1 and 2. Based on that, if I put it here, 1 and 2 value, what I will get, I can relate it with this matrix part because I'm calling the element, okay? And I'm finding the multiplier which is A21 by A11. That multiplier, you multiply it negatively with row 1 and add it to second row. If you will do that, this first element will become 0. Okay, so that's the logic. Then in the second step, I'm doing UA J comma all, right? So this selects the second row, all column, right? So this is basically selects the entire second row here, and then it removes, so the multiplier. So first row, now this is UA I comma all. So this shows the first row. For right now I is 1, multiplier is done, and then you get the element 0. So that way you have first made this element 0, okay, for the second row part. Now again what will happen, this for loop is here near at the end. Now j value will increment by plus 1. So instead of 2 it will become 3, okay. Then again you will find new multiplier which will be A31 by A11. Okay, that multiplier will be multiplied with the row 1 and added subtracted into the row 3, and you will get this element 0. Okay, so once your this secondary for loop ends, you have reached this step. Now in the second step will be to further reduce the another element and make it 0, right? In that case, now your the first for loop comes. Now I have used I equal to 1. Now I will use I is equal to 2. And based on that reference, you will again multiply this, and at the end you get the row echelon form. So that way, I get a row echelon form. So this is my Gauss elimination method. So let's say I call this method Gauss GUU, Gauss elimination of A. Right now it's showing not a number because they are linearly dependent. So let's say, let me select a proper value like this part. So here we have been given matrix A. Let me select this. So my A is equal to this. And if I do Gauss elimination A, this is how my upper triangular matrix will look like, right? So I have made all the lower triangular part as 0 and I'm getting the upper triangular matrix, right? Makes sense? Now this is one part of Gauss elimination method. So what we learned here was that first you transform your matrix into the row echelon form, and based on that then you compute the coefficient value, right? But here I have to use A augmented B. I have to do row echelon form into A augmented B, not A. So then let's find the solution. Let me create one more function. Again, I'm using the previous copied part and I will just explain it because we don't have much time to go through everything, right? So here, so this function, what it does is finds the solution to this linear system of equations via Gauss elimination method. So you have to provide augmented matrix C, which is the combination of A comma B, right? So A is your coefficient matrix, B is your constant matrix. Now this function, which is solution to Gauss elimination, first you find the upper triangular matrix of this C, A augmented B part. Like here, I have matrix A and my A and B combined. So this is A augmented B. I am doing row echelon form and finding the upper triangular part, right? So I'm calling this previous function that we created, it creates upper triangular matrix. Now, here what we are doing, once we have this part, what you do, you multiply this matrix, the transform coefficient matrix with the your XYZ equations and correlated with the new constant matrix data, right? So I multiply Z with 1 is equal to 0, I directly get it. Then 0 into X plus 1 into Y plus 0 into Z is equal to minus 12. And based on that, you get the value of I. Here it's directly, other coefficients are 0, so you can get directly the value. But for some other case, uh, like here, you first get minus 2 times Y is equal to minus 6. So you get the Y value. Then you have to substitute X and Y in the first equation. So 1 time X plus 2 time Y is equal to 8. You have value of Y which you found, and now you have to find the value of X. Okay. So you are going from bottom to top and finding the coefficient value. So once my upper triangular matrix is ready, what I will do, I will extract out how many rows and column I have. Now, what we learned was that here your X is number of variables that are that are given by how many columns you have in your system, right? So row comma 1 size of 3, row comma 1, since I'm using 2 and 3 part. Yes. So right now I'm creating the matrix, vector matrix X, which is a your variable matrix or variable vector, let's say. Okay. So I have created by zeros. It creates a number of rows and columns. Column is 1. Now the final element. See, the last element is given by last element of UA divided by the second last element of upper triangular matrix. So again, this logic, let's try to relate it here, that here if I want to find the value of Y, it will be given from I minus 6 divided by minus 2. So this is minus 6, which is the final last element. Okay. So it's given by UA row bracket column. Then UA row column minus 1. So that becomes your second, this element, and you get the final value. Once you know the end part, okay, now you have to go backwards. So I'm going I row minus 1 in the negative direction and finding the xi value. So again, if you want to understand this logic, just put the value of I and write it down, what exactly it's doing. So it's calculating the equation backwards and then you are getting the final value, right? Uh, so let's look at this A and B value and see what solution we get. Clear all PLC. This is my A and B. I'm creating augmented matrix C as A colon B. Then I will call solution to Gauss elimination method and I will put the function C, and this is my answer, right? 2, 3, minus 1. My coefficient values are x, y, z values are this, which will satisfy system of equations where constants are given by matrix B and coefficients are given by matrix A. So this was the idea. I mean, this is the idea of how to solve this system of simultaneous algebraic equations, right? But now let's say, uh, that you don't want to. I mean, we have computed this because we know the method, but you don't always have to code this out, right? So there are inbuilt MATLAB commands also which you can use to find the solutions of this equations. So in MATLAB, you have not here, linsolve command. Just give me a minute. So you have this linsolve command. What it does, it solve, as it mentioned, that it solves uh, linear system which is represented by ax equal to b, and it uses this LU factorization method. Again, don't worry about the method. It's similar to your Gauss elimination method with some tweaks. Okay, so you provide the matrix, coefficient matrix and the constant matrix, and you get the solution, right? So same example, see, we found with Gauss elimination solution is this. So I can do lean solve A comma B, and see, I'm also getting the same solution, right? So you don't have to always write the code out. MATLAB has this inbuilt solvers which are available that you can use it. Okay, this we solved it to get the idea of how exactly the solution works and to utilize our coding knowledge to understand how this simple matrix calculation can be coded, right? See, it's very simple part, but when you have to set a logic in Gauss elimination method, you have to identify this part, like how you will convert this simple matrix into row echelon form, and that too you have to write it into generalized way. Okay, same way, when you are once you have the row echelon form ready, how to compute the variable value by back tracing. So again, we have to write this generalized part. Now, obviously, MATLAB has this part already ready with this lean solve part, but you also need to understand because not always you will have such sort of a facilities available. In that cases, you have to understand how exactly this mathematical solution can be translated into the program part, right? I can also solve the same problem by doing A inverse B, right? So inverse of A into B, I'm also getting the same solution. So then other options you have, one is lean solve, inverse. You can use backslash operator also, which I think we had previously also discussed. That answer to, let's say, is A backslash B, and I'm getting the same solution. So here see, both of these methods are actually doing the inverse of matrix A and then giving you the data. But remember, when you have a much bigger system size, then doing inverse is much expensive. So rather I will utilize lean solve or LU factorization method. Okay. So you have LU part also. So if you will see help LU, this gives you the upper triangular matrix and a permuted lower triangular matrix L such that your A becomes L into U. And then you can use this L and U part to further solve your problems, right? So this options you have. So what you can do is again try to understand this code part where how we are utilizing our programming knowledge to code out the Gauss elimination method in a functional form and how we are finding the solution. If you are not still sure about this method, just look at some example, try some problems by hand first. So you will get the logic and then compare that logic with what we are doing in this function part, right? Once you do that, so that way you will also develop the correlation between mathematical expressions and the numerical methods and the programming part. Okay. So this was the idea about how we can solve a system of linear algebraic equations, right? But again, we said that we will come to the chemical engineering problems and we will try to utilize our knowledge to solve the chemical engineering problems. So let us look at this multi-component distillation column example. So here you have been given a flow diagram where you have feed coming at 17 mole per minute flow rate, which has four components because I can see from x1 to x4 and the mole fraction is of feed is given. First distillation column, it splits into two parts, your top distillate and then bottom raffinate. It further goes into the another two column and then you have further distillate 1, distillate 2, raffinate 1 and raffinate 2. You can call it top or bottom portion also, right? So this is the flow diagram for a separation process of benzene, toluene, styrene and xylene. So 1, 2, 3, 4, four components you have and it has been given what is the final specification for all these columns, right? So mole fractions are given. Now, what has been taught to us, like what has been informed to us is that process was running at a steady state at 17 mole per minute flow rate. However, due to failure in a master feed pump, the feed flow rate drops from 17 mole per minute to 20 mole per minute in a stepwise manner. So let's consider that every 1 minute the flow rate is cut by -5 mole per minute part, right? The molar consumption composition of distillate and bottom remains the constant throughout, assuming no transient in the system and the equilibrium is maintained when the flow rate is reduced. Report how the production rate of each feeds get affected, right? So here we know the mole fraction, but we don't know what is the D1, B1, D2, B2 value, right? So now let's say when we are at steady state, you can just write down this all the mass balance equations for all four components, right? So you have your four components and then for four components you will have four overall balance. So four, and to that you will have four equations where four unknowns, four equations and four unknowns, right? So that can be solved and you will get some solution, but that is at steady state. Now what they are saying, there is some issue in the feed pump. So let's say before this distillation, from whatever location the feed is coming, there are some issue and then you have to reduce the flow rate. So how this top and bottom flow rate will change? So we have to find out that, right? So let's look at, let's try to code this part. Okay. So we will do it in a stepwise manner, which is finding molar flow rate of distillation column. So this is our goal. Here we have two mass, sorry, here we have overall and component mass balance options, right? So your overall mass balance will look like feed is equal to bottom, let's say I'm calling it distillate plus bottom portion, right? So this is how it looks like for a one distillation column. Then, so this is overall mass balance. Then if you want to do component wise, so let's say fraction, molar fraction of component I into feed is equal to molar fraction of component I into distillate. Let me call it as X D X F sorry X F X T plus X B I into P. Okay. Everything is same. Can you understand this? That if I want to, let's say, solve the component balance for, let's say, first component. So, molar flow rate of the feed into the molar fraction of that component, XFI into feed, is equal to uh, mole fraction into the distillation, mole fraction into distillate flow rate plus mole fraction into bottom, mole fraction in the bottom product into the bottom flow rate, right? So that way, this is component mass balance. Now you can use these equations to get the system of to get your what is this called? Sorry, to get your system of linear algebraic equation that we will solve it, right? So here we have this. This is how it looks like. Uh, let me start with this clear all and CLC part. Now what we will do here, create a matrix, create a matrix A and B such that it represents one's system of equation as AX equal to B, right? Now, so if you will try to see, let's consider the first example here. Okay. Mass balance of component A, component 1. This is how it will look like, that you have 0.2, 0.2 into flow rate 70 is equal to 0.35 into D1 plus 0.16 into B1 plus 0.21 into D2 plus, sorry, yeah, 0.01 into V2. So this is how your component balance will look like. So now your D1, B1, D2, B2 are nothing but your variables that you want to find. So correlating with AX equal to B, your X is D1, B1, D2, B2. Okay. My coefficient matrix A. So A is the mole fraction. So A will contain, so A row will become the mole fraction of component 1 across multiple streams, right? Second row will become mole fraction of component 2 with across multiple streams. Column you can interpret as mole fraction of all component in D1, okay, B1 and D2 respectively. So you can put this and you have to put all this part. So first row will look like exactly like this, 0.35 space point, I can write comma 0.16 comma 0.21 comma 0.01. Then second row will look like 0.54, 0.42, 0.54, 0.54, 0.42, 0.54 and 0.1. Same way, I'm just copy pasting it from here. Yep. So this is how my coefficient matrix will become. Now constant matrix. So constant matrix is from this part, which is mole fraction in the feed into the total flow rate. Now, so it has to go to component wise. So 0.2, 0.4, 0.25, 0.15. So I have 0.2. Now 0.4, 0.25, yeah, 0.15, and I can directly multiply 70 outside, right? So this gives me the constant matrix D. Now here you can see A is 4 cross 4 matrix where you have 4 equation and 4 unknown, and B should be 4 cross 1 matrix. So that's why I have created the column wise part, right? Be very careful how you are defining rows and columns, else you will get an errors, right? Now once I have this, I can find solution to our problem. X is equal to, right? I can use linsol A comma B, right? And then you can run it. And this is how your solution is. But this is at steady state. Okay, so this is at steady state. And what we have been asked, like if flow rate is decreasing, then what will be the value? And so we have to find that. Okay, so for that part, what we will do, I will run one for loop which starts from feed is equal to 70. It's reducing in step size 5 and going till 20, right? So from 70 to 20 in step size of 5. So this is my main for loop in which I will do the further calculation. So here my coefficient matrix, which was earlier B, will look like this. See, what we have been told is that molar composition of distillate and bottoms remains constant throughout. Same way, feed molar fraction is also constant, right? So only the feed value is changing. So instead of 70, I can put F. So initially it will start with 70, then go to 65. Every time my constant matrix will change. Okay. But my A matrix is remaining constant. So my solution will change and it will become linsol A comma B. Okay. Right. Now you can print this also, F printf, and say the flow rates at F is equal to %d slash m f r, and then I can just print display the X part, okay? Or I can write, instead of saying, I can write this way also. You can do F printf. I can say B1, B1, B2, B2, and I'm doing display X dash. So X, since it's a column vector, it will convert it into the row vector and I will get the value this way, right? So the flow rates at F equal to 14 are given as this. Okay, sorry. Let me put slash n and then, right? So I'm getting this value. This is how it will change. At F is equal to 17, this will be the flow rates. Once it goes to 65, it's going down. Same way till F is equal to 20, this is how it will change. And this will be my final value. Right? So you can write it that way. Now, another way could be, I can plot it out. So this was just a tabular form. But instead of tabular form, let's say I want to put it in much into pictorial form, right? So then I can use the plotting commands to plot it out. Okay. So let's look into that, and we will also look how fine tune this data rather than just representing in this manner. Okay, just give me a few seconds, please. So right now what is happening is, in our code we are finding the value of X, but we are not storing it. It's going away within the for loop. So for different flow rates, we are computing the value of X flow rates, we are displaying it, and then we are forgetting it. But if I have to plot it, I need to store this data. I need to store this data somewhere, right? So for that, what I will do is, rather, I will create one solution to X as a zeros. I will create one matrix. Its size will be, so I know I have total 4 stream data, and each column will represent that stream data, but each row will give me that stream data at particular flow rate. So for that, I have to find this part also, that how much it's changing, length of F, and I can use that, so this length of F as this part. When I'm finding this, I can put solution to X, the given row, comma, all components is equal to X. Okay. So what I'm doing, I'm storing the X data, I'm finding the X value, and I'm storing it into the solution X part. Okay. Uh, for the printing part, let's say I want to print it much nicely, so I can use this part. So I have this flow rate percent F at Fn D1 D1. I'm just printing it this way, or you can just use the display X step. Now can you see solution to, just give me a minute, sorry. F dash publish. This is just F. So this is how it will look like. For a different flow rate, I am printing out the value. Okay, correct. Now here this solution underscore x also contains the data. It's not updated well. Why? Oh yeah, because the loop is incorrect. So instead, I will use an I loop. Okay. Uh, Let me copy paste this part and explain it here. So I'm starting with fprintf. Corresponding flow rates are this. I have already defined the flow rate vector f, which is going from 70 to 50. I'm running an I loop which starts with 1 and goes to the length of f. So how many step size we will have? 70, 65, that way. My matrix B is computed. B is equal to this into Fi. X becomes clean A sol B, and solution X becomes I comma all row and X comma this part. F printf flow rate. This is how I'm printing. So this is just much nicer way of printing it. Now this solution X contains all the data. I can put this. So this is my D1 flow rate, how it is decreasing, D1 flow rate, how it is decreasing. So then what you can do is I can call the plotting command. Okay, I'm just copy pasting it, but it's very simpler part. Now I'm plotting the variation. So first I'm plotting F, which is change in the feed flow rate. What is the stream data? Instead of stream data, I have solution to X. Okay. So you can see the all row, and the first column represents the D1 part, second column represents the B1, third D2 and fourth B2. And if I run it, yeah, this is how your plot will look like. Okay. So change in D1, B1, D2, B2 with decrease in flow rate. So initially when you had flow rate of 17, this were the value. Now once it's decreasing and becoming 20, these are the corresponding value, right? So that way we are analyzing how the change in the flow rate is affecting the my solution. Okay. Let me just put some nomenclature here. Right. The flow rates where, right? And if I run it, this is how it will look like. Okay. So much nicer way compared to the previous one, right? So that's what it. So in this class, what we understood was when you have system of linear algebraic equations, right? First is how to identify whether what kind of solution we will have. So for that, you have to use the rank condition part. Okay. You have to look at the rank of matrix A and A augmented B, and based on that, you can decide whether you will have a unique solution or the infinitely many solution. Then we learned how to code out this Gauss elimination method to find the solution to this linear simultaneous algebraic equations. Okay. We also learned the we compared that data that result with the inbuilt MATLAB option, and then we looked at this mass balance example across the distillation column. So now you can also consider the other examples also, like mass balance in liquid-liquid exchange sorry, liquid equilibrium. In extractors, you have same mass balance data. In absorption column also, right? In leaching example also. So again, there you will have multiple components. For each component, you will put out this series of equations. Okay, so you will have system of linear algebraic equations, and then you can put them into this algorithmic part and then find out the solution. Here we also understood like how change in the feed flow rate will affect our results, right? So same way you can try out different things. So let's say you have liquid extraction example I'm considering. Like you have data for some extractor, right? Now you, instead of changing the feed flow rate, let's say you are changing the feed composition, and based on that also you can find out how the product composition will change. Okay, so that's the idea with this coding part. You can understand and learn about the system, how it will behave under different scenarios, right? So that was it for today's class. I will stop now. I will stop the recording also. If you guys have any doubt, do let me know. Else we will continue it from the next class, where we will learn about the solution to non-linear equations, and where we encounter that part in chemical engineering problems, right? So if you have any questions, you can ask me. Else we can stop.